great pleasure to introduce Daniel Holz, who has actually been, you see that he has Stanford on his title slide. That's because he's a visiting professor here for about 6 months. And it's been great to have him here, and I think he's still here for 6 more weeks or so. It's been too short, but we've managed to start to work together on Gravitational Wave project.
That's right.
So Daniel did his PhD at the University of Chicago, and he was a postdoc at the Kavli Institute for Theoretical Physics, and then back at Chicago, where we almost overlapped for like a month, I think.
Yep.
And then he was at Los Alamos for many years before starting back again as a professor at the University of Chicago. Shortly after that, he joined LIGO, and he's really played a key role in a lot of what's happened with LIGO, in particular in interpretation of some of their most exciting results over the last 2 years. So it's a pleasure to have Daniel, and welcome.
Well, thanks. All right, let's see if this works. Well, thank you. So first, can you hear me? In the back, yes, nods? Great. Okay. No? I gotta know. Louder? I can move it up, but it's already pretty. Okay. Well, you'll definitely be able to hear the chirp at least. That's good. Okay, any better?
Yeah.
All right. Okay, we'll try this. Okay, it's great to be here. Thanks for having me. As Risa mentioned, I'm on sabbatical here. I've been here since January. It's been really, really nice. This place is awesome. I've gotten a ton of stuff done. You know, here's a photo biking across campus the other day. Lots of new collaborations. I'm here for about 1 more month. Please visit me. Oh yeah, let's see if this works. Oh yeah, it does, okay. So I'm in PAB 246. And you know, I mean, as you all know, this place is amazing. Every time you turn around, there's someone interesting to chat with, all sorts of new ideas. It's really been incredibly invigorating. So thank you for having me. That's the main message of the talk. It's really been great. Okay, all right. You also, you really have made me sort of sing for my supper. I've given, I think this is my 4th talk since I've been here, roughly 1 a month. I gave a Blackboard talk shortly after I arrived, which was kind of a more technical talk. And then I gave a Chi-Pac-T talk, more astrophysics focused. And then a colloquium, SITP colloquium last week, where I kind of focused on GR and black holes. And I'm giving a public lecture in a couple weeks. And I've tried to make each one of these talks different. So this talk is not going to overlap with those previous 3 talks. And I'll kind of highlight the areas where other interests I have as I go along. Also, I look back, you've heard a lot about LIGO. There was a beautiful colloquium by Vicky Calagera just a couple months ago, and I look back in the archives, and I mean, it just seems like everyone's come through and given a talk about LIGO, including there's another one this week by Lara Cadenati up at SLAC. So, and I should mention, you have your own LIGO group. It's an experimental group. And in particular, I've chatted quite a bit with Brian and Ricardo. I've learned a lot. They're definitely the experts on the experiment. I encourage you to go visit them. The lab is really cool, and it's just across the way. And their logo is amazing, and I think all Stanford LIGO people should be required to tattoo that on their bodies. This tree is the actual 150914 waveform. It's brilliant. So, okay, so I am not going to talk about the instrument basically at all, because you have your own local experts. All right, so basically I'm going to skip all the pleasantries. You've heard all this many times, so I'm not going to go through, what are gravitational waves, what do they do, what are black holes and neutron stars, why are black holes, in some sense, the most profound objects in the universe, what is LIGO, how does it work, why is it certainly one of the most amazing things ever built, ever conceived of, why was 150914 such a big deal? Black holes exist. That alone, I think LIGO has now conclusively shown that. I think that really is, I mean, if you stop and take a deep breath and think of what that means, it's remarkable. The black holes agree with Einstein's theory from 100 years ago. That's also remarkable. This is all a great story. You know, we could go through all this, but I'm going to kind of skim that. But if there are questions, I'm happy to go back. If you want me to come back next week and give another talk on this, I'm happy to do that too. But I'm going to kind of focus on one thing. And what I'm going to focus on is 170817, which is this recent event, this binary neutron star event. So that's going to be the story I'm going to focus on today. And the plan is to kind of go through some of the background, how we detected it, you know, what we actually detected, some of the other observations that went along with it, and then discuss some of the astrophysics and cosmology that comes out. So that's my plan. Okay. And I should say, of course, you know, interrupt with questions as I go along. It'll help me kind of adjust the pace. Okay, so I'm going to start sort of at the broadest level. You've probably all heard about 170817. It's revolutionary, that's a pun. Right? This is really a major development, I would claim, in certainly astronomy, certainly in the GR community. This was the first time we'd ever both heard a source and seen a source. And heard, that's we always talk about hearing in terms of gravitational waves. I can explain that if there's interest later. But this was the first time that we both saw it in light, and then we heard it in gravitational waves. Okay, and you know, the sound comes first. It's just one of the oddities of the way this stuff worked, at least in this particular case. Okay. And then from this, because we'd never been able to do it before, we learned a lot of things. We learned things about the nature of GR and relativity, fundamental tests of relativity. We learned about the origin of gold. We learned about the age of the universe, all sorts of interesting things. And I'm going to kind of highlight a few of those as I go along. Okay? But this, the bottom line is this is something that was never done before, and it really heralds a new age. Okay. All right, so what I'm going to do is to actually go through each of these kind of in turn. I'm going to start with the actual detection, and then I'll move on. And so I'm going to kind of break it into little segments. And the first one is what we actually detected in gravitational waves. All right, so this is what we detected in gravitational waves. It was a beautiful morning in Chicago, and this was, you know, August 17th. And there was a chirp. And so you're going to see a number of these. And what you're seeing here is this is frequency, this is time, and each of the sort of color here is, you can think of it as how loud it is in that little frequency time box. And you know, mostly this is noise. It's kind of, you just get little things kind of show up just all the time in your detector. But I'll draw your eye to this very suggestive track here, and that track is a source. And I should say, even this image, when this came through, and I should say this is the Hanford detector, when this came through, this was already amazing because you can see it by eye. And usually you can't see, what our expectation for all these sources is you would never be able to see them by eye on this, or it'd be very unusual. You'd have to do very sophisticated analysis to pull out of all this stuff an actual signal. But in this case, you can just see it. And so that got people pretty excited, but nothing happened in the sense of there were no automatic triggers. We have this whole very sophisticated system where text messages get sent out and we all get woken up and we go rushing to our computers because LIGO might have detected something. None of that happened. It sent, you know, a message to a few people saying, oh, there was something interesting in one of the detectors. But only in one. And, you know, there's all sorts of noise. These detectors do not behave all that well, sorry. They're okay. But they're not perfect, and they're always kind of jumping around. So having a detection in one detector is not that big a deal. It's probably just noise. And so a few people, you know, got this. And the natural thing to do then is, well, I mean, this is really suggestive. Most of the noise in the instrument doesn't look at all like this. So what you do is you go and you check the other detector. And the first person to do this was actually Reed Essick, who's a postdoc in Chicago, and he checked the other detector, and here's this nice track, and then there's this huge glitch. And glitch is a very fancy term for something we don't really understand that happens every now and then for a very finite period of time. And so something happened in our detector. This happens like once an hour or so, various amplitudes. And it's like a fiber twanging or something, I don't know, anyway, this happens. Because this happens, our very sophisticated analysis pipelines say, wow, look at that, this is vetoed. This time window, there's nothing interesting there. And you just move on. And that's why, since there was a veto, we didn't trigger, none of the other stuff happened. But Reed noticed what hopefully a lot of you have noticed, there's a beautiful track underneath. And the second, he saw that, he was the first person to realize, well, we've detected, and if you've looked at these enough, you immediately know that's a binary neutron star. So we've detected a binary neutron star. And not only that, it's a really loud binary neutron star, because you can see it by eye. That track is pretty clear. So that was pretty exciting. So what you can do, so we immediately set to work and removed that glitch. If you remove it, there are different ways to do it. The simplest is to just notch it out, but you can do more sophisticated things. There's your track. And it's, that's gorgeous. And everyone can appreciate that's pretty nice. Okay, just this track in this one detector is significant, well, it's louder than 150914, which was that insane first detection, which was ridiculously loud. And that's the combined signal to noise of both detectors for 150914. This one detector was already louder than that. So you knew right away this was a good one. This is a keeper.
To make this, did you interpolate that out? Interpolate out the glitch?
Yeah, so for this particular plot we did. You can fit the glitch because it's so well described. I can pull up a plot later if you're interested, that you can actually fit out the glitch. It's a very well-behaved glitch, and then get some of the data underneath as well. Yeah.
So is Livingstone louder than Hanford was?
Yeah, for this event it was. Yeah. And so here I think I have, I think I might even have the numbers shortly. Okay, so this is great, but there are actually 3 detectors running at this time. Virgo had just turned on a couple of weeks before, which was kind of a big deal. The reason we were still operating in part was to wait for Virgo to turn on, just so we could say that we had operated in coincidence, even though no one really expected anything to happen, or at least I didn't. But it was a politically expedient thing to do, so we had 3 detectors running. Here's Virgo. And, by eye, there's really no beautiful track. And by sophisticated analysis, there's essentially nothing there. Okay. And the thing is, at first blush, this is a problem, because we have the loudest event by far that we've ever detected in gravitational waves in the other 2 detectors. How can it be completely quiet in Virgo? And so your first thought, well, at least my first thought, most people's first thought would be, well, Virgo was just turned on. It probably wasn't working, right? How could there be nothing? Virgo's broken. Okay, except 3 days before, we had another detection. This was what we call the black hole rain. In August, we just got inundated with systems. It was just a disaster. And this was one of them, 170814. And what was interesting about this system was it was a triple detection. It was the first time we detected something in Hanford, Livingstone, and Virgo. And so, this is more like what tracks are supposed to look like. There's kind of a fuzzy thing there. Your eye doesn't jump out. But when you do the analysis, there's no question there's a signal there. And everything fits. This is a triple detection. Virgo is working as advertised. Okay. So now you go back and you ask, and so at the end of the day, what we seem to have is, this is where we're at. We have these beautiful tracks in Hanford and Livingstone, nothing in Virgo. The effective SNR is 2, which by our standards is really essentially non-interesting. But the combined SNR is still very high, 32, That's astronomical. And the false alarm rate for this, the idea that this could be noise, because we get noise, every now and then the noise might look like a signal. The chances of this being just pure noise is less than 1 million. You don't have to do anything very sophisticated to know that this is not pure noise in any reasonable universe. So that's where we're at. As an aside, so it must be arranged somehow so that Virgo doesn't detect it. And that turns out actually to be a gift, which we didn't realize right at first. The fact that Virgo has no detection at all is extraordinarily useful, and this is why. It's because it's a function of the antenna power pattern. So if you have a gravitational wave detector, the detector doesn't hear uniformly over the sky. It hears from some directions better than others. It has a sensitivity pattern, just like your ears. And so there's some places on the sky, for example, right above the detectors. So I should say one thing. So this is a sensitivity pattern. So blue here means not very sensitive. Red here means quite sensitive. Most sensitive is sort of normalized. This is in Earth coordinates. It's fixed to the Earth. And so above North America, which is right in between Hanford and Livingstone, we're quite sensitive. And also through on the opposite side of the Earth, because it's all symmetric and gravitational waves don't notice the Earth. And then there's some places, for example, down the diagonal of a detector, if you think from symmetry, if you have a gravitational wave detector like Hanford, it's an L-shaped. If you're down the diagonal, by symmetry, nothing can happen. And so we have no sensitivity at all. That's these blue spots. Okay, so this is kind of advertising where we're heading, but here is the localization that we get from the detectors, and this is the sensitivity pattern. And what you notice is, for Hanford, this is Hanford, it's kind of very close to the most sensitive part of the sky. Now I'll switch to Livingstone, still very close to the most sensitive part of the sky. Now here's Virgo. It's very close to the dead spot. And because it's so close to the dead spot, it helps us localize. And that localization was small enough that we got to do a lot of other stuff. And that's what really has made this event sensational. Okay. All right. So, so that's the kind of detection part. But okay, what was it? What have we actually detected? And so I'm going to just spend a few slides and go through that. So we have this clear detection. What is it? Okay, so I think this is mandatory, and this is going to be a little loud right at the end. What I'm going to play is the sound of this event. So it's the actual waveform, and we're just putting it into the speakers, amplified by 20 orders of magnitude. And you will just be able to compare it, and we'll just play it in the time domain. So just as a function of time. And what you're seeing here are the other events that we've detected so far. 150914 was the brightest event, the loudest event, that first event. It was quite massive, 3030, and you can see that because it merges pretty quickly. It doesn't stay in band very long. The farther along you go on this, that means it goes to higher and higher frequency, and that means you're lower and lower mass. So if you look at where these merge, you can instantly see this is the lowest mass of this set. Also, the amplitude here is related to how loud they are in the detector. So if you kind of integrate up all this signal, that's pretty loud. It's pretty high. This one, it has more cycles, but it's small enough that it's actually not even above our threshold, and we can't be sure it's real. So, okay, that's what we had so far. Now I'm going to play you 170817. Okay, let's see. There we go. So there it is. You can see it's a little different. It kind of goes longer. So for 150914, we had 8 cycles, and then it merged, and it was done, gone forever. For 170817, yeah, there are a few more cycles. It's oscillating back and forth here, and it's still going. And you can start to hear it now. And it's still going. And I'm just going to play the whole thing. I mean, this whole time it's in our detector. It's not usually this loud this early, so it's probably get some good resonances. So it's still going. You know, all the others were less than a second. Okay, so that's 0817. Okay, it's much. It's really different. And what that is it's much higher, it stays much longer, it emerges at much higher frequency. And that tells you it's a much lower mass event. Okay? And you know, that integrated sound was what was so loud. Okay, and I should mention this movie is done by Ben Farr, who was a postdoc in the group, is now faculty at Oregon. All right, okay, when you do an analysis of that, and this is kind of a sophisticated analysis, you don't have to do such a sophisticated analysis if you just look at kind of what that chirp, the way that chirp evolves and where it seems to end, you get this too. But if you actually do a sophisticated analysis, this is what we call parameter estimation, and this is an estimate of the parameters of the binary system, and this is the mass. M1 is by convention the mass of the more massive companion, and M2 is the less massive one. And there are a lot of details here which you can ask me about later if you're interested. These are correlated. We don't measure the mass ratio that well. But what you can see is the support here is all, 1 to 2 solar masses in both cases. Okay? Unlike all the others, which were 5, 10, 15, 30, this one is just in this 1 to 2, okay? Which is extremely suggestive. Here's one way to show how suggestive it is, and I think Vicki showed this exact same plot. Here are the black holes that we've detected so far. So these were LIGO black holes. Here are the kind of other black holes we know about from X-ray binaries. All I'm plotting is their mass. The x-axis doesn't mean anything here, it's just aesthetics. But you can see the black holes that we've detected so far are kind of higher mass. Is there a way to dim the lights in the front? All right, there.
Too dark?
No, that's fine. That's fine.
Okay, all right. Yeah, that's more, okay. So here are the LIGO black holes. Wow, this is really bright now. Okay, and here are the other ones we knew about. So these are higher mass, which is interesting. That's another interesting story. Here are the neutron stars that we knew about. And as you may know, neutron stars are expected to be in the kind of 1 to 2 solar mass regime, and most of them are. Maybe they go a little higher. That's very controversial, but this is where you expect them to be. And here are the two ones we just detected. Okay, right smack in the neutron star regime. Okay, and the only reason I'm going through all this is just from the gravitational waves. All you get are the masses. And so just from the masses, we said, well, it really looks like neutron stars. We're going to call them neutron stars. We'll put that in the title. We'll put it in the abstract. We'll make a big fuss that they're neutron stars. However, just, in full disclosure, I'll just point out that we, at least when we did this initially, we did not know that these were neutron stars. They easily could have been black holes as well. The waves, the gravitational waves, are identical until the very last moment when the neutron stars start to deform. And so this is a plot that kind of summarizes this, where this is what's called the deformability parameter, which you can think of as just if you have a tidal field across an object, how much does it respond to that tidal field? And in these units, black holes are down here at the origin, and if you're out here somewhere, that means you are getting stretched by your companion, which means you're not a black hole. And what we'd love to do is be able to say, oh, we're out here somewhere. Because not only does that say this is not two black holes, but it tells you the equation of state of the neutron star, which is like this fundamental physical observable. It's something you really would love to be able to measure. For this one, at least at first blush, at the first pass of the analysis, we couldn't rule out that they were black holes. So the fact that we call them neutron stars is because of the suggestive masses and because there's clear evidence that there were some baryons in the system. And I'll get to that next. Okay. All right.
Could they have merged into a black hole?
Yes. So so the question was, could they have merged into a black hole? And that's a very interesting question. Again, from the gravitational wave side, we don't know what happened at the end. From the theory side, we would think they probably did. The only question is, how long did it take to make that black hole? When you merge two neutron stars, you could get a heavy, sort of hypermassive neutron star for a while. And there's some thought that maybe that happened for a little while, and then it collapsed to a black hole. And that turns out to be a completely fascinating topic, which we can talk about after. Okay. So the next part of this story is due to Fermi. And of course, you're all very familiar with Fermi here. This is what starts, so already, I would say at this point, that just the discovery in gravitational waves was, a big deal for our community. This was what LIGO was built to do. This is what a lot of us were waiting for. And it was such a emphatic, beautiful event that we could have stopped there. But the story doesn't stop there because Fermi was operating, and this is what Fermi saw. So here what I'm showing is that same plot. Here's the LIGO event, and it merges. And then about 1.7 seconds later, you get a spike of gamma rays. So this is Fermi, and this is Integral, which is another satellite. And that's a detection. Okay? And just for the record, you might say, well, it kind of bounces around. Maybe that's not real. But if you do the analysis, you get two things. There's a time coincidence here, and in essentially all three channels, and the sky location is completely consistent. What I'm showing here, this green thing is what comes out of LIGO. This sort of purple thing is from Fermi, and this is a joint Fermi integral timing measurement. And they all overlap. And the probability of that happening just from chance is, less than 1.10 to the 7. So it's real. It's an association. Okay. Now, just as an aside, because this is something, again, I'm not going to spend a lot of time today on, but it's also incredibly fascinating. This is a very unusual gamma ray burst. We have a distance estimate, even just from the gravitational waves immediately, we have a distance estimate. I'll talk more about that later. And if you infer the kind of isotropic luminosity, it's orders of magnitude below many of the other GRBs. So we detected a burst of gamma rays, but this burst of gamma rays is unlike any other one we detected to date, where we had a confident estimate of the isotropic energy. So this is very, very interesting, exciting, and suggestive, and this is going to be a big business going forward. Okay. And I'll just say one other thing, just because I think it's one of these very elegant measurements that it just immediately kind of captures why this multi-messenger astronomy is kind of this whole different, you can just do these novel probes. So you can now, for the first time, just ask, okay, I have gravitational waves, and I have electromagnetic waves, gamma rays, and I can ask, do they travel at the same speed? Which was not a question I could have asked before. And I just told you, well, the gamma rays showed up 1.7 seconds late, which sounds pretty bad. Light's pretty fast. They showed up 1.7 seconds late. Now, the thing to remember is they were emitted a long time ago. We were at 40 megaparsecs, over 100 million years ago. This was emitted, and it's been traveling that entire time. Okay? So you could imagine they were emitted at exactly the same time, and over 100 million years, the gamma rays slipped by 1.7 seconds. And if you assume that, you get something like this, 1.10 to the 15. They're within the sort of speed of the gravitational waves, and the gamma rays are within 1.10 to the 15, which is pretty close. If you assume in the most pessimistic models, you could say maybe the gamma rays were emitted 10 seconds later, and they've spent all that time catching up, and now they're within 1.7 seconds, and soon they'll overpass, actually pass through and be ahead. If you take that, then you're at, also at 1.10 to the 15. Which is all to say, what we get, and you can do this basically in your head. The first time, most of us did this in the collaboration, it was in our head. It's the back of the napkin. Okay, you go from not having any measurement at all to having a measurement that's good to 15 decimal places. And it's not very often in science that you get that kind of leap. It's also, just for the record, it's a very interesting bound, because it turns out in many theories, it's very popular nowadays to modify gravity, and I might talk more about that towards the end. If you modify gravity, one of the generic things that happens is you mess up this relation. And so by confirming that these really go at the same speed, you rule out a bunch of theories that a lot of people were working on. I mean, this, caused a lot of heartburn in a fairly, quite a large community, because, we've shown that gravitational waves and light go at the same speed, which is what the straight GR predicts should happen. Yeah.
Are there any constraints from the dispersion relation of the gravitational wave?
Yeah, so in general there are constraints. This is the effect of just the arrival time. You can also ask, does the arrival of the different gravitons, if you like, depend on frequency? And so if it did, then you would get, say, the lower frequency things arriving, at a different, probably later than the higher frequency thing. That would shift the waveform. And so we have measurements of that, and that again can be related to graviton mass and all those things. The measurements are actually better for 150914, so we can talk about that after. But yes, that's another thing you can do, and then I'll talk about yet a third thing towards the end if I have time. Yeah, okay. But this is just straight off. You have this event. You've now made, this definitive measurement, which is going to take us a long time to really significantly improve over, and it matters. All right. Okay. So, but we're not done. And actually, let me just, okay. So there's one more chapter to the story, which is now in the optical band. And so we had the gamma ray burst. That's pretty good. But since this was the first time we knew, so because they're gamma rays, we were pretty sure there was matter, it really made sense to go and look and see if we could find anything else there. And in particular, we really wanted to find the host galaxy. So I'm going to just tell you a little bit about that story. It starts by noting the localization. So what I'm showing you here are the 90% localization regions for some of the LIGO detections. And what should draw your eye is that 170817, this one I'm talking about, is much smaller than these others by an order of magnitude or so. It's about 30 square degrees, which from a gravitational wave perspective is like pinpoint accuracy. Like, that's amazing. From an astronomer's perspective, that is ridiculous. No one can, that's like just saying it's over there somewhere. It's literally like it's over there. It's way bigger than a full moon. Telescopes are, a couple of orders of magnitude smaller in fields of view in general. This is not something you can really do much with, except that there are certain specialized telescopes that can do searches for this. So I just want to point out that one of the best ones is the dark energy camera, which was used for the dark energy survey, which RISA played a major role in. And that turns out to be an ideal instrument to look for transients, because it has a very large, by these standards, field of view. It takes big pictures on the sky, many times the size of the full moon. So we had, even before I joined LIGO, I had a meeting, and I'll explain later. I've always been very interested in finding counterparts to gravitational wave sources, because there's a lot of science you can do with that. So I ran a meeting at Chicago to bring LIGO people and observers together to try to do this, to come up with ways that we might be able to find these things on this huge swath of sky. And at that meeting, a number of us realized, the dark energy camera is perfect. And so I started a collaboration with some people to use it to follow up gravitational wave triggers. And we followed up the first few events. The 150914 event, we scoured the sky, we saw nothing, and published nothing. And then we did that a couple of other times, where we've looked, we just don't find anything. They're binary black holes, we don't expect to find anything, but we want to show we could do it. And it turns out it was really good practice. So we fired up this program. So at this point, we're already kind of delirious. We got the gravitational wave detection. We've got the gamma ray burst. We're already doing various calculations. But I spent that entire day planning to do the follow-up. This happened morning in Chicago time. This telescope's in Chile. So we have to wait until night there, and then we can point. About 10 hours later, sun sets, and we can point. And we have to have everything set up. This is how we did it. This is just to show you, this is actually the footprint of the CCD. So this is the camera. This is where we take our pictures. Each of these is one picture. And we covered the localization region. And then we started to look at the data. And so we did this by eye because we were really in a hurry. And it takes a while to do things in a very effective automated way, and we wanted to do it immediately. So we picked the brightest galaxies and we just looked at them by eye. And Ryan Chornock sent this email, and he noticed that something had appeared. I should have done this in a different order. This is before and this is after. And it really helps to have the circle, but there's something there. There's no question. And I'll just say Ryan Foley, who was a member of our team, he did this independently and he beat us. He had also pointed at a smaller telescope. He just had a much smaller field of view, just pointing at the brightest galaxies. He also found it. So, Ryan Chornock sent an email saying, we got it, this is amazing. And we thought we had made the big discovery. And then Ryan Foley immediately contacted us and said, oh, I got it too. I got it like a half hour ago. And then, it was pretty great. And then things just kind of went crazy. And just, again, let's see, I don't know why it's doing that again. Okay, hold on. It's worth seeing again, but Okay, there we go. All right, and this is just another picture of this. Again, this is not that big a field, but here's the before and here's the after, and you can see it's very clear. Okay, so emphatic detection. And then, essentially every telescope that could pointed at this thing across all bands. We immediately called up the director of HST, got time, pointed at everything. Anything, everybody was going to let you use their facilities. And so I would claim this is almost certainly the most observed transient in history. 87A, a nearby supernova, also a lot of people looked at. But this is really, everyone did. It's amazing, so thousands of people ended up observing this. And it's still going on, I should say. So we're still observing in X-ray and in radio. The story gets ever more interesting. It's really been fascinating. And just to give you just a little teaser, but again, I'm not going to focus on this. This is what the light curve looks like for this star. So basically a star appeared and then disappeared. Here's the light curve in different colors, and these solid lines are kind of a basic theory of what that might be, called a kilonova. And this is related to this whole story about where the gold in the universe comes from. And even in the first paper we wrote on this, you can just see that everything kind of works, and you can estimate the amount of gold, and you can show that this is where all the gold in the universe comes from. That's kind of a side thing, but it's pretty cool. So it's just one of the things we learn. All right. Okay, so I have about 20 minutes remaining, a little less. Okay, so what I thought I'd do now is kind of go through. So I should say, just from the DES side, from this DCAM group, we produced, just right at the time of announcement, we had 8 papers kind of exploring all the repercussions, ramifications of this event. Here's a little movie where you can see it appear and then disappear. Okay, so this was a lot of work. Of course, LIGO, we also produced a lot of papers on this event. And my group was involved in a lot of these, but I'm going to highlight one because it's sort of my favorite, and it's the one I'm sort of proudest of, which is this one, which is this first standard siren measurement. So I'm going to spend a few minutes and tell you about this. I think it's a pretty nice story. Okay, so standard sirens. And it starts, so just to give you a sense of what a standard siren is, standard sirens, the key observation here is that black holes are super simple. And they really are. In terms of physical objects, black holes are as simple as you can get. They're described by mass, spin, and maybe charge. And that's it. Macroscopic object, fully described. Like, that's it. There's nothing else but those numbers. And so if you have two of them, you can predict it's fairly straightforward to predict what's going to happen. And what you end up with is an expression like this, which is a chirp mass. There's one scale. And that scale comes from, if you can think of it as you have the quadrupole formula, which is something that comes straight from Einstein's theory. It was written down like 1917, which tells you the emission of gravitational wave energy. And then you have Kepler's laws, which tell you what the binary is doing when the binary is far apart. And then you just do energy conservation, and you end up with a very distinct pattern, where what happens is you get faster and faster. The frequency shifts up as you go forward in time, and it gets louder and louder. The amplitude goes up. And that's called a chirp, and it's defined by relativity. GR says the chirp must look like this in the early inspiral. Then as you get close to merger, it gets a little more complicated, but that also can be kind of understood more or less nowadays. But that's fixed by relativity. That's just physics. Okay, so what that means is, since you have this very clear prediction from relativity, you can use an observation of this, measure the chirp, and back out the distance. And that distance is coming straight from relativity. It's just calibrated by the theory. There's no astrophysics, there's nothing, this is all, you can do it all paper and pencil, and then if you observe a gravitational wave source, you know how far it is. Even if it's to cosmological scales, you just measure it directly. And that's extraordinarily useful in astronomy and cosmology, because as you may have heard from, Varus, in fact, I think we had just, Dave Spergel gave a talk on this, measuring distance is hard. But in the gravitational wave game, measuring distance is easy. However, we don't get a redshift. So if you want to know the redshift, which is how you really do cosmology, the recession velocity, if you want to know, say, the expansion history of the universe, you want to know the expansion rate right now, you need to measure the velocity. You get that from the light. And it's relatively straightforward to measure that from light. So if you can combine these two measurements, you can, for example, solve this very complicated equation and figure out what the Hubble constant is, which is the rate at which the universe is expanding. Okay? So all you have to do is measure both of these. And needless to say, that's what we did. And so I should say I've just spent a lot of time working on this. The idea was originally Bernie Schutz's idea, a prescient paper 30 years ago, where he said, you could do this. And the way he was thinking about it, you did it statistically. So we subsequently showed that if you had a counterpart, you can do much better. And we call them standard sirens. And then we then realized gamma ray bursts were a really good way to do this. And then I just I spent a lot of time, I've written tons of papers, trying to kind of lay this out as something you could do. And the truth is, I joined LIGO because I wanted to make this measurement. I put together the whole thing with the observers. It's nice to figure out where the gold in the universe comes from and all the rest of it. But what I really wanted to do was do the standard siren measurement. And that's why I put it all together. And needless to say, 170817 is the perfect standard siren. I couldn't have asked for anything better. It was incredibly loud, high SNR, which means I got a very good measurement of distance. I had this very clear optical counterpart. It was incredibly bright, impossible to miss. There's a nearby galaxy. You can get the redshift of the galaxy. The first time I did this, I just, Googled the redshift. Like, you just put it in and it comes out. Like, it's just a known galaxy. So you just get the redshift for free. You can immediately make the plot. And there's one, in fact, this source is too good. It's too close, and there's some details of peculiar velocities, which I can talk about after if there's interest. So, after all this, basically that evening, I could make my plot. So here's the plot. And yeah, that's beautiful. Well, you should all be in tears. It's really perfect. So this is the Hubble constant. I'm applying the Hubble constant, and this is just our best guess for what the Hubble constant is from LIGO, from this one event. And to draw your eye, I've put a green and orange band. The green band is the state-of-the-art measurement from the cosmic microwave background. So the Planck satellite says this is what the value is, like 68 or so. And then the orange band is the state-of-the-art measurement from supernovae, which are completely different. Using type 1a supernova, it's a completely different way to measure this. You get that orange band. Now, the discerning among you will probably notice that these do not overlap. And there's a greater than 3 sigma tension between them. So it just turns out, and this is causing a lot of consternation within the community. Now, our event is right there, and it falls right on top, which is a miracle. I mean, it really should, these error bars say it could have been anywhere. The 1 sigma is like pretty wide. The fact that it's right between them and doesn't prefer one or the other, pure chance. Okay? But the fact that it's here and not way out, Hubble was way out here. His original value is out in the other room. And it took a long time to get down all the way down to here. And this kind of consistency, yes, they're not, they're inconsistent, but only at, a few percent. That's impressive. It took years, it took, billions of dollars to get there. And we did it with our very first event. Here we are, it's all consistent. And I think I find it, quite impressive. I mean, you could just say, well, physics works, and that's true. Physics, works. But, it could have been anywhere. And it's right there. And, anyway, and, there was no fiddling. That's just where it is. Okay, so that's pretty neat. There's some other stuff which, let's see, I have probably about 5 minutes, right? So I'll just point out that the errors come from a distance inclination degeneracy, so there's a lot to do here. You can turn it around and make statements about gamma ray bursts. It gets very interesting. And so there's been a lot of work just kind of following that through. Oh, and I'll skip that. Okay, all right, in my last few minutes, I'll talk about some other things. So that's all great, but I just want to give you some sense of what this new field is about. So we had this discovery, and just in the last few years, we've gone from this is all hypothetical to actually having data, having detections. And so it's become this very active, vibrant field. And just to give you some sense of this, I thought I'm just going to show you some of the papers I've done with my group just in the last year. So here are some papers from the last year. These are kind of the black hole focus papers. And some of them have to do with how do you make these black holes. This paper, I guess given the time, I'm just going to describe them. This paper, we show that there's a universal distribution of spins when you make black holes out of smaller black holes. And we essentially showed that the LIGO black holes aren't made out of smaller black holes, which is interesting if you think the black holes are dark matter, and I can talk a lot more about that. We use Gaussian processes to improve the way we do this. That was, and I should say this is something I've been discussing with someone here on campus in the CS department. We talked about spin as a way to probe this. I might actually talk about the big black holes. This is just the black hole stuff from the last year from my group. There's also all the sort of more EM related papers from my group from the last year. And I'm not I mean, it's a very productive time. We've got our first detections, and it's like the sky's the limit. It's like this incredible playground. And this is what it's kind of been like being here. Every time you turn around, you come up with some new idea for an interesting measurement that you can do that you could never do before. And so here are some of the papers. So I think what I'm going to do, I'm going to pick 2. I have 2 minutes, so I'm going to pick 2. And then Risa is going to push me off the stage. Okay, so I'll just talk about the Hubble constant 1, just because I really like standard sirens. This is just showing you the evolution of this tension. Actually, this is from Wendy Freedman, who gave a talk here a few months ago. So what I'll do is I'll just cut to the chase, which is you can ask, how well does LIGO do measuring this? And this is a recent paper with 2 students, Xinyu Chen and Maya Fischbach, where we kind of go through and say, here's how well this is going to go going forward. So what we do is, as a function of the different runs of LIGO, here's the error. And to guide your eye, that's what you care about, is this level here. At that level, you can resolve this tension, this discrepancy, and you can say who's right. And that is design itch over year 1, which is a fancy way to say in maybe 3 years. We have our first. We're off now. We'll turn back on in January. We'll run for maybe a year. We'll turn off for a little bit. We'll turn back on, and then we should have a measurement. The combined measurement from all our sources will adjudicate this discrepancy. And I want to say one thing that may not be entirely obvious from all this is the thing about the gravitational wave sources is it's calibrated by relativity, which means we really understand every step of the way intimately. It's sort of perfect. It's just a beautiful way to make this measurement. So the systematics are more or less under control. The systematics you'd worry about have to do with response to the instrument, which are things we can test. And so it's a very robust way to measure this. And at the very least, it's very complementary to all the other ways. I want to say superior, but that just gets me in a fight. So I'm not going to say that. It's just a very nice complementary thing to do. And then I guess I'll end with just the flip side of this, which is a recent paper where what we did was you notice in this case, what I've just told you is, well, we measured the Hubble constant, we got the right value. And what that tells you is that the gravitational waves and the light did the right thing. They went, and which, by the right thing here, I mean is they went through the same universe. Which sounds like a pretty obvious thing to say, but again, I talked about modifications of gravity. If you modify gravity, which is a good thing to do, to try to do, because we have this dark matter and this dark energy, we don't really understand what that stuff is. If you could explain it away by modifying gravity, that would be very compelling. So a lot of people have tried to do that. When you do that, one of the ways to think about it is you modify things so maybe you get something equivalent to an extra dimension. The gravity leaks out, which makes it look weaker at large scales, which maybe might explain the dark matter. There's a whole story involved with the way this works. We can now test this, and we can test it on cosmological scales, which wasn't possible before, where you can just ask, does gravity leak out? And the answer is no. It seems to work, at least on these scales. So out to 40 megaparsecs, the gravity is behaving exactly the way we expect. The gravitons and the photons, if you like, are going through the same universe, and you can just measure the number of space-time dimensions. It's 3 plus 1. There it is. It peaks around 4. And there's some details here, and there's some stuff that I'm kind of sweeping under the rug, but this is kind of a generic thing. This is, it all fits. Everything fits. And that's, again, a novel thing. You're measuring the number of space-time dimensions just from this one event. Okay, I'm going to do one more slide, and then I will end. I'm going to skip over all the Gaussian process stuff and all the rest of it, which is just, I just want to mention, this is just a paper we put out yesterday. Again, this is with Maya Fischbach and Will Farr. It's just, again, this is an example of the sort of thing we can do. And I did this for RISA because I think this is, and it's related to some of the stuff we've been talking about. This is just looking at the evolution of the rate of mergers. Okay? And so what we're doing is we're just asking, how often do black holes merge? And what we do in this paper is we ask that, are they merging at the same rate here nearby as they are farther away? And the reason that's interesting is because all the models of how you make these black holes predict that there should be more earlier in the universe. So the question is, can we measure that? And can we measure where they peak? And can we measure the delays? And this is all related to the formation of these systems, which is related to, what's interesting, it's related to the very first stars in the universe. So by measuring the sort of death rattle of these black holes, you're actually learning about the very first stars, which have what we call low metallicity, which formed in the early universe, which then merged to make them. And we showed that, this is with the data we have so far published, and there's no evidence for any evolution. But as we get more, we've shown, in a couple of years, we should be able to tell you, does this go up or down? How fast does it go up? What does that teach us about stars in the universe? So it's just a completely fundamental relation of where these black holes are coming from. And no one's done it before. Now we get to do it. Okay. I just want to put up the slide for the group. This is the EU Chicago LIGO group. So Ben Farr, who made that movie, is now at Oregon. Zohair Doctor did a lot of the work with the dark energy camera, trying to line that up, get it to work. Xinyu Chen has really helped also with the EM follow-up work and designing that and working on the Hubble constant stuff. Maya Fischbach is involved in the standard siren stuff, and also a number of other sort of astrophysical projects. Reed Essick is a KICP fellow at Chicago. He's the one that first noticed the chirp in Livingston, and he works on a very broad range of LIGO-related things, including, we're working right now on detector characterization and trying to use astronomical sources to calibrate the detector, which is really cool. Andrea Bryant is working on population synthesis in the group, and I'm most proud of this. Bob Wald, who some of you know, who's definitely a theorist, never gets anywhere close to data. We've managed to kind of entice him into the dark side, and he's now involved in LIGO and was even on one of the LIGO papers doing work on testing gravity. Okay, and so I'm just going to end. The future is loud and bright. It's extremely promising. This is just the very first step in this new era of astronomy, right? This multi-messenger era of gravitational waves and light. There should be many more. Right now we're off. We should turn back on in the new year sometime at an improved sensitivity. The rate should be at least triple what it is now, what it has been so far, maybe even more. So we expect to start getting bombarded with events. We'll see what happens next. Okay, I'll end there.
Okay, questions?
What temperature did they get up to? What do we know about that? The neutron stars when they collide?
I have no idea. That's a good question. The temperature, I mean, again, that must be related to the equation of state. And so, yeah, I don't know, but it's, we could probably figure it out because it's, our process nucleosynthesis, which I think is, requires pretty high temperatures, but actually that's not even the highest. So, I mean, actually this relates. So my guess is we don't know. Not just I don't know, but we don't know. And to give some sense of that, I think this is interesting. I mean, just, it's a very nice picture, and this is actually the movie of what's supposed to be happening. So you take two neutron stars, you collide them, and then, stuff happens. Okay, but you could take a neutron star and a black hole and collide them. Now that's, if you think about it, a very different physical system. Right? Strictly speaking, right now, we don't know which of those is happening. And you could make all the light that we've seen colliding with a black hole, which is, you have two of the hardest, most compact objects in the universe colliding at half the speed of light, or you have this hard object colliding with nothing, just space and time. That seems very different. We can't tell them apart, which gives you some sense of, how much there's still to learn here. It's because all the material gets ripped off, and the stuff we're seeing is the outer part. So, we don't really know what's happening way at the inner. I mean, we'd like to. It's probably related to the gamma rays in some way and the time delays, and that's something for the future. Yeah.
Did you say from the spin of the initial black holes that have emerged, you can tell that they didn't come from mergers themselves?
Yeah.
Can you tell me more about that?
Yeah. So the idea here, it's very interesting, and it has to do with GR. So you have two black holes. If you merge two black holes, the final black hole has to be spinning. And so we showed in that paper that there's a sort of a universal distribution of those spins. And to get some intuition, what's happening is you have these very compact objects, these black holes. They can get very close before they merge. There's a lot of orbital angular momentum there. You can't shed that orbital angular momentum. So if you're making it out of a binary coalescence, you end up with a black hole that's spinning. Okay. Now, if you're making it out of a star that collapses, maybe it spins, maybe it doesn't. We're not sure. You could easily make something that's basically not spinning. But if you're making them out of black holes, it has to spin. We derive the distribution. Then you can ask, are the LIGO black holes consistent with being drawn from that distribution? And the answer is no, not really. I mean, we only have a few. We don't measure spin that well. It's a sort of statistical statement, but
They don't spin enough for what?
they don't spin enough. The LIGO, from what we can tell, and there's another paper which I could show where we do the first estimate of the spin distribution. I can, since I'm responding to a question, it's okay.
While he's responding, are there any students who want to ask the next question?
Anyway, this is, so just to show you, here's the universal distribution. And you have to draw from that distribution. And this is, 0.7 is, so basically you end up spinning around 0.7. You can get far, the best you can do is if you have maximally spinning, there's a maximum spin to a black hole, which is basically if it's, the horizon's going at the speed of light, you can't go any faster, sort of. So there's a maximum spin, that's out here at 1. 0.7 is pretty high, and that's where you have to be. And what we don't do spin that well, but so far the population is consistent with all being around here or less. And we don't have any evidence of anything up here yet with 5, 6 events. Who knows? This could all change. In 6 months, I could be up here saying, yeah, they're all made out of black holes because there's a peak at 0.7.
Any students? One more chance for students before I call in one more. Oh, okay, there's a question there. Yeah, go ahead. Yeah.
Okay, I'm going to assume.
I know, but
So, are there any optical methods to find candidates? Like you see these gravitational lensing effects in the videos?
Yes.
Is it possible to take videos of those? Can you really see those effects?
Okay, so you mean to actually get a video of up close. So there's a project to do that called the Event Horizon Telescope, where they're doing long baseline interferometry and trying to image the black hole at the galactic center. Okay, and that it has 2 advantages. One is it's a supermassive black hole, so it's much bigger, and it's really close. It's at like 10 kiloparsecs. And with that one, using the absolute state-of-the-art, you might be able to get a few pixels and see kind of what they call the shadow of the black hole. That's the closest we can get. That's already complicated. For these, the angular resolution is beyond anything. Black holes, and the real message is black holes are super tiny. It's very hard to wrap your mind around just how small they are. And so, you take the sun, the black hole is a few kilometers across. You're now putting that, even 30 solar masses, which is a big black hole by our standards, is 30 kilometers across, and you're putting it at the other side of the universe. It's, yeah.
okay, I'm going to end on time, but let's.
About your animation on your last
Yes.
slide. Can you just describe step by step?
Sure. Sure. Okay.
Show Neutron star spinning around and merging.
Okay, so this is an artist's conception. 30 seconds, 3 seconds. Okay, so this is the 2 neutron stars. They're emitting, you can see the gravitational waves going out, then they merge. This is supposed to be the kilonova. That orange thing, that's kind of fast. I'll go right. The orange thing was the gamma ray burst. This is the radio and X-ray emission, which comes from the material hitting the medium outside. So here, the neutron stars, those are the gravitational waves being emitted. They collide, that was the gamma ray burst. This is now the kilonova, which is where we do all the art process, we make the gold, and then much farther out, you start hitting other stuff and you generate X-ray and radio. That X-ray radio part is also a mystery. Well, mystery is too strong. It's a raging debate about exactly how that works. It just turned over. It's been growing all this time, and now the X-ray and gamma rays are just starting to decline for the first time, and we're monitoring that, and then now you get to have all your different models and try to figure out what's really going on. That's also an incredibly fascinating, rich topic. Yeah.
All right, thank you very much. And just to say one more time that Daniel is still here for about 5 more weeks.
July 5th.
So
Come visit me,
come talk
please.
to him.
It's skeptical claim that all the gold comes from Neutron.